Now let T1 and T2 be two unbiased estimate of a parameter theta. Then T1 is said to be more efficient than T2 if the variance of T1, okay, here T1 and T2 are what? Two unbiased estimates of the parameter theta. So T1 and T2 are, in other words, they both are statistic. And then T1 is said to be, that is statistic T1 is said to be more efficient than the statistic T2 if the variance of T1 is less than the variance of T2. Okay, in other words, we can say that the variance of T1 is less than variance of T2. What does that mean? The concentration of values of T1, that is statistic T1, about the true value of theta, that is about the true value of the population parameter theta, will be greater than that of T2. This is why we say that T1 is more efficient than T2. So we may also say that the variance of an estimate decreases. The variance of an estimate decreases means its efficiency increases. Okay, now let's have a look at the relative efficiency of T1 with respect to T2 with respect to T1. And this is how we write that variance of T2 divided by variance of T1 is called the relative efficiency of T2 with respect to T1, and it may be used to compare the efficiencies of the estimate. Now let's move on to a problem. x1, x2, etc., xn are some as a random sample taken from a normal population with mean mu and variance sigma. Now we are asked to find out that there are three statistics that are given over here. Sorry, not three, more than three. That is T1, which is equal to x1, T2 is equal to x1 plus x2 divided by T2, divided by 2, etc. up to Tn is equal to x1 plus x2 plus etc. xn divided by n. Now we are asked to examine whether the estimates are unbiased, and we are also asked to compare their efficiencies. Okay, now these statistics are proposed as the estimate of mu. Okay, so let's first check whether they are unbiased estimators of mu. Okay, so for that, now how to check the unbiasedness, I hope you all know, but again I will show you how to check the unbiasedness with regard to this particular problem. Now for that, let's have a look at our first statistic T1. Now here T1 is equal to x1. So in order to check the unbiasedness, what we usually do is we usually take the expectation of T1, which is equal to expectation of x1, which is equal to, and it is said that these statistics are proposed as the estimate of mu. So expectation of x1 is equal to mu. So the first statistic is an unbiased estimator of mu. Now what about the second? T2 is equal to x1 plus x2 divided by 2. You take the expectation of T2, then that is equal to expectation of x1 plus x2 divided by 2. Take that 1 by 2 outside. Expectation of x1 plus expectation of x2. Now again in the question it is said that it is proposed as the estimate of mu. So 1 by 2 into mu plus mu, which is equal to 1 by 2 multiplied by 2 mu, which is equal to mu. So therefore T2 is also an unbiased estimate of mu, then, or the population parameter. Similarly we can say that expectation of T3, expectation of T4, etc., expectation of Tn, all the expectations of these particular statistic are equal to mu. So you can write this as expectation of T3 is equal to expectation of T4, etc., is equal to expectation of Tn, will be equal to mu. Okay, therefore you can conclude that all the estimates suggested in this particular question are unbiased. Now our main agenda is to look at the efficiency. So for that we will consider variance of T1. Now what is variance of T1? We know that T1 is equal to x1. So variance of T1 is equal to variance of x1, which is equal to sigma square. What about variance of T2? Variance of T2 is equal to variance of x1 plus x2 divided by 2, which is equal to, you take the constant outside, so in the case of variance it will become 1 by 4, variance of x1 plus variance of x2, which is equal to 1 by 4, sigma square plus sigma square, that is equal to sigma square divided by 2. Now etc., variance of Tn is equal to variance of x1 plus x2 plus etc. plus xn divided by n, which is equal to, you take the constant outside, you get 1 by n square, variance of x1 plus x2 plus etc. plus xn, which is equal to 1 by n square, sigma square plus etc. plus sigma square. You have n sigma squares over here, n times, so this is equal to 1 by n square, n into sigma square, you will get the answer as sigma square divided by n. So in short, what can you say? Now here variance of T1, sigma square, is definitely greater than sigma square by 2, right? So sigma square by 2, and sigma square by 2 is greater than sigma square by 3, etc., and so on. You can say that it is again sigma square divided by n minus 1 is greater than sigma square by n. So from this you can conclude that T2 is more efficient. T2 is more efficient than T1. What about T3? T3 is more efficient than T2, and so on and so on. And finally we conclude that Tn is more efficient than T1, T2, etc. Tn minus 1. And I hope you got why we conclude in this way. Why? Because the variance of Tn when compared to the other variances of other statistic, it is much lesser. Okay, so that is why we say that Tn, the statistic Tn, is more efficient than the other statistic that is given in this problem. Okay, now let's move on to another problem. Here x1, x2, etc. xn is a random sample from a normal population with mean mu and variance sigma square. Now the statistic given here is T1 x1 plus x2 minus x3 and T2 2x1 plus 3x2 minus 4x3. Now you are asked to compare the efficiencies of T1 and T2. So before moving on to comparing the efficiencies, let's find out whether this is an unbiased estimate of the given population parameter mu. Now in order to find out the unbiasedness, let's have a look at the first statistic. So the first statistic T1 is equal to x1 plus x2 minus x3, and expectation of T1 is equal to expectation of x1 plus expectation of x2 minus expectation of x3, which is equal to mu plus mu minus mu, which is equal to mu. So T1 is an unbiased estimate of the population parameter. What about T2? T2 is equal to 2x1 plus 3x2 minus 4x3. Calculate the expectation. Expectation is equal to 2 into expectation of x1 plus 3 into expectation of x2 minus 4 into expectation of x3, which is equal to 2 into mu, that is 2 mu plus 3 mu minus 4 mu is again equal to mu. So this is also an unbiased estimate of the population parameter mu. Now we have to check for the efficiency. So in order to check for the efficiency, we'll have to find out the variance of the first statistic, that is variance of T1, which is equal to variance of x1 plus variance of x2 minus variance of x3, which is equal to sigma square plus sigma square minus sigma square, minus sigma square. Again, this negative value, we are converting this into a positive value, since variance will always be positive, and so this is equal to 3 sigma square. Now variance of T2, which is equal to variance of 4 into variance of x1 plus 9 into variance of x2 plus 16 into variance of x3, which is equal to 4 sigma square plus 9 sigma square plus 16 sigma square, which is equal to 29 sigma square. So in order to find out the efficiency, we have to check the quantities over here. So here it is clear that variance of T1 is less than variance of T2. Therefore, we conclude that T1 is more efficient, or T1 is more efficient than T2. Now the relative efficiency of T1 with respect to T2 is given as variance of T1 divided by variance of T2 is equal to 3 sigma square divided by 29 sigma square, which is equal to 3 by 29. So this is the answer. I hope you have understood what efficiency is and the problems also. Thank you.